Many of the values we use to describe the physical world are exact. Whole numbers and simple fractions allow us to define lengths and quantities that are predictable and easy to handle. But the square root of 2 behaves differently. Instead of stopping at a specific point, its decimal form expands, 1.4142136, and so on, without ever reaching a final digit or settling into a repeating sequence. While engineers and physicists can work with finite approximations of this number, rounding these digits changes the identity of the value. In a pure mathematical system, the moment we truncate that expansion to fit a screen, we are no longer working with the true root. To maintain the exact value of an irrational number, mathematicians developed a set of procedures that allow us to manipulate these infinite sequences as symbols, keeping their true identity intact throughout a calculation. These procedures require an understanding of how numbers are categorized. Like different species, numerical values live in specific families based on their internal properties. This diagram maps out the relationship between those families. While we spend most of our time with natural numbers and integers, this isolated zone marked Q star contains the irrationals. These values appear the moment we calculate the diagonal of a square or the properties of a circle. They are a necessary part of geometric calculation, even if they are more difficult to represent than standard fractions. Because these roots are unavoidable in higher-level mathematics, we use a specific series of operations to standardize them and ensure they remain workable within our equations. The first operation is decomposition. Large, inexact roots are often composite values that can be simplified into smaller, more efficient components. Consider a value like the square root of 50. Instead of converting it to a long, messy decimal string, we can look for a way to rewrite it using its internal factors. The notes show 50 broken down into 25 and 2. Identifying a perfect square, like 25, simplifies the radical. The square root of 25 is 5, moving outside the radical. The result is 5 root 2, a perfectly exact, manageable value. This process creates a standardized unit. It takes a large, cumbersome quantity and expresses it in its most efficient form, which makes it much easier to compare and combine with other numbers later. Once these roots are in their simplest forms, they must follow specific operational rules. These constraints ensure that the symbolic logic of the equation remains consistent. In equation A, we see the rule for addition and subtraction. You can only combine these terms if the numbers inside the roots match. 5 root 6 plus 2 root 6 minus 4 root 6 equals 3 root 6. If those inner values were different, the operation could not proceed. Multiplication follows a different set of constraints. The values inside the radicals can be different, but for them to merge, the index, the type of root being used, must be identical. As the first example shows, when we multiply roots with the same index, they combine under a single radical sign. 8, 20, and 10 are multiplied together to form one larger product inside the root. These rules act as guardrails. By defining the exact conditions under which these values can interact, we maintain mathematical precision, even as the numbers themselves grow more complex. A final challenge occurs when an irrational root ends up in the denominator of a fraction. Attempting to divide a value by an infinite, non-repeating decimal makes further manual calculation nearly impossible. These notes show 3 divided by root 2. We clear the radical from the bottom through rationalization. Multiplying the fraction by root 2 over itself targets the denominator without changing the value. The irrational part cleanly moves to the numerator. For more complex denominators involving addition or subtraction, we use a conjugate, a mirrored expression that causes the radical terms to cancel each other out. Rationalization is a matter of algebraic formatting. It rearranges the components of the fraction so that the infinite parts are positioned where they are most useful for the next stage of the calculation. While the starting fraction and its final form look different on the page, they represent exactly the same quantity. The difference is purely a matter of organization and utility. Mastering these operations allows us to perform complex translations. We are taking a symbolic representation that is difficult to use and converting it into a standard format used across mathematics. By using these rules, we carry the full precision of an infinite value through an entire equation without writing its decimal expansion. These procedures allow us to maintain order within our notation. By following these rules of symmetry and substitution, we can work with the infinite within the practical constraints of a finite system.